going to sketch a normal curve. We got the middle where z equals 0. We always, when we sketch it, we label our z axis. And at the top here, we have our highest point on the curve. Now we then label equally spaced points on the right, at least 2 points, probably just 2, and 2 points on the left, labeling them from -2 through 2 with 0 in the middle. Always. Z is always labeled like this. Okay. At the z equals 1 and -1, we make a point that's 60% as high as the central point. And you've seen the formula for this curve. And you've been asked to understand why, at least using the formula to verify that that 60% would be right. And then here between an 1/8 and a 1/7 of the height, and then we try to sketch a nice symmetric curve. Mine never come out all that symmetric. That's a little better than average for me. Now my 60% I think might have been just a little high. It looks like maybe 63 or 64%. That's okay. We're just using this to represent the normal curve. And as long as we get a reasonable representation, we have a picture that we can work with. Now often on a normal curve, we're using it to represent some other thing, some other quantity, x. And what it really represents is probabilities that z will lie in various regions of this curve, and that would correspond to probabilities that x lies in various, within various regions of the curve. X would be, I don't want to go through all the detail on this, but at the middle, the value of x would be the mean value of x. Okay, and then at z equals 1, that would be the mean plus the standard deviation. And this would be the mean plus 2 standard deviations and so forth. So, using as an example, let's let x equal 16 and let standard deviation equal, let's just say 2. Okay? Well then the mean is 16, which means that 16 goes here. Mean plus a standard deviation, that's 18, goes here, because if we add the standard deviation to the mean, that's what we get. We move another standard deviation out here, we're at 20. Going this way, we're going to be at 14, and we're going to be at 12. So, when x equals 12, z is -2. When x is 18, z is 1, and so forth. So, now what's the interpretation of the curve? Okay, well, let me just shade in a region. I'll keep my chalk over there, so I've got to keep walking in front of the camera to get it. You'd think I'd have a little more foresight than that, but we'll just take what we've got here. Okay, I want to take some region of this curve. So I'm going to take the region between, let's say here and here. I'm going to shade the region under the curve. Now you understand that if you knew what the z value was here and what the z value is here, you could evaluate your n of z function and you would get a trapezoidal, you could do a trapezoidal approximation of this area, right? So we could do a trapezoidal approximation of this area. If we want a better approximation, we could break that region into a bunch of smaller trapezoids so that the segment at the top of the trapezoid would stay closer to the curve. But we could estimate its area. And then we could get a good approximation of its area using the function n of z equals 0.4 e to the negative z squared over 2. Now that's a very close approximation. The accurate is n of z equals 1 over the square root of 2 pi e to the negative z squared over 2. And 1 over the square root of 2 pi is very, very close to 0.4. If you use this, you have much less than a 1% difference between what you'd get if you used the accurate number. And you can never be completely accurate in evaluating 1 over the square root of 2 pi anyway, because pi is an irrational number. Okay, so for our purposes, the 0.4 is okay. That's where it comes from. And the reason we use the 1 over the square root of 2 pi, or the 0.4, is simply that that's the number out in front that will make the total area under this thing, all the way from negative infinity to infinity. The total area under this whole curve is 1. So I can say, okay, total area is 1. Also, as I've said, the reason for this comes from what you get from coin flips. You do a histogram of the number of possible heads. Well, you already have a pretty good approximation of a normal curve when you do that. You go to a large number of heads and you approach an infinite number of heads and look at the shape of the histogram and do a little bit of much more advanced mathematics with that we can't even begin to talk about here. and you get the normal curve. Okay. Now, the important part of the interpretation is the area here corresponds to the probability that a given value of x will lie between here and here, wherever here is on the x scale and wherever here is on the x scale. So the area is a probability that x will fall between, and I'm all out of room here, here and here. Okay, now that's not a very definitive statement, but intuitively, okay, the probability x will fall between here and here is equal to this area. And you can approximate this area by a trapezoid. Or you can chop it up into as many little trapezoids as you like and evaluate those and add them up and find that area as accurately as you like using this formula. And you can get accurate enough for almost any purpose just using a 0.4 instead of the 1 over square root of 2 pi. Now the question becomes, okay, that's great. If I know the mean of x and the standard deviation, how do I relate the values of x to the values of z? Well, let's talk about that just a little bit.